Okay. Okay, so hello, welcome back to one of my video log recording sessions where I talk about genetic algorithms. And today, since I kind of finished talking about using different distributions for sampling of the utility values and the constraint values, well, kind of finished, and then found out that I needed to find a new way of evolving things, a new evolution scheme. That's what I'll be covering today. And then I could probably move on to well, using that new evolution scheme with, or applying that new evolution scheme to the distribution products. But I don't know if another 60 hours of constant running on Google Colab Plus is worth the money or not. But anyway, and let's not forget that I started this because I wanted to know why dips happen. It all started ever since I started looking into dip sizes and dip size percentage and stuff like that, and down the rabbit hole I go. But anyway, so today I am briefly going to look at what happens with the current evolution scheme, and to do that I'll be looking at the peak plateau plot. That is this, by the way. This is for 10 items when using normal distribution for both the utility values and the constraint values. And today in this session, I'll only be sticking to using normal distribution, only for this session. And then once I feel that I have a better evolution scheme, then I'll probably apply that to other distribution products. I've said that like 3 minutes ago, didn't I? Yeah. Anyway, so here's what happens with the current way that I evolve things. With 10 items, in the peak plateau plot, we can see that both the peak level and the plateau level go up. However, they're not as high as I would like them to be, and also the dip. The dip size increases towards the end as the maximum constraint percentage goes up. Similar for other distributions as well. But anyway, and then at 40 items, the peak level, the plateau level, just stops above a certain point, past a certain point, and so does the peak level. And relative to the maximum, relative to the total sum of utility values, it is slightly more than half. So this is 2500 out of 4000. So that's like 62.5%. 62%, which is not ideal, because ideally, if the maximum constraint percentage is 100%, you know that you can carry everything, so it should be going up, all the way up. Maybe never touch the red line, but it should be going up. Same for when we have 100 items. And in my last videos, I have concluded that this is due to the fact that no entities were being struck out by the selector function, because the total sum of constraints that each entity had were all below the threshold that the selector was enforcing upon. And since no entities or very few entities are being struck out, there are little to no new entities being born through procreation. So every kind of innovation or improvement, overall improvement, was the mutation's job, and that always has its limits. So that's why this happens. So I needed to find a way to make sure that new entities would still be made when little to no entities were being struck out by the selector. And to illustrate, or to rather show you that was what was actually happening, I'm going to go to one of the previous notebooks, Python Jupyter notebooks, and just go through step by step what happens during the evolution stages, and just point where I could have done better or what I did wrong. So there we go. So we first choose as I know what I'll do. I'll just take a screenshot of this. So here, during the very first phases, I select, a maximum constraint percentage is selected over here, and the total constraint is set, which is the maximum constraint is set here, and this is what the selector will be using as this threshold. And there are 20 of these maximum constraints, 20, and per maximum constraint there will be 5 iterations of the evolution. Okay, and then we make these values, and then we start the actual evolution here for generations, which is usually set to 500, because I found out that 500 generations is enough for even until 200 items or 200 genes. So let's take another screenshot of the next part. So we just started here, and we have the world. Oops. Well, I forgot this part now. The world is empty, but it is now filled with the genesis. The genesis is full of void genomes, void entities, entities with void genes, just an easier term, an easier word, just all zeros. They contain no they are genomes, or rather entities, that say that they are carrying none of the items or none of the genes, that none of the genes are actually activated. So they have that. So this is like usually there are 1000 entities, and for example, if it were 10 items, no, let's just say 40 items. 10 is too small and it gets confusing. So it's 40 items or 40 genes. So 1000 entities, and each entity would have 40 zeros in it, and it's a Python list of 40 zeros. 40. And we have 1000 of this. And that's the genesis, and then genesis is put into the world. So now, what happens after that, after the world is actually populated by 1000 genes, we put the world through the selector, meaning that as we have the world, the selector will just find and weed out or strike out the entities that go above the threshold, the constraint threshold, or the maximum constraint. So, but in the very first generation, or generation 0, because no entity is actually carrying anything, none of them will actually get struck out. Okay? And then what happens? And then we do this. It looks, even for me, this looked quite complicated, even when I wrote it. And then I realized, after having read this like 30 times, I realized that all of this procedure can be just called the ranking phase, or the ordering phase, or the sorting phase, whatever. What this does is sort them in order of highest to lowest summed utility values for the entities individually, and have them in a dictionary so that I can sort them by key, because the key is the key in the dictionary called entities dictionary, ENTTS dict. The key is the summed utility value of that entity, and the value is the list of entities that have that that correspond, that would have that summed utility value. And then we again flatten the dictionary into the world again, so that it becomes a list again. So the world was a list, and then it got transformed into a dictionary, and then was sorted in reverse order, which is highest to lowest, and then this dictionary got converted back into a list. Okay, and then we and then I would get the current population. So, for example, in some generation n, there were 1,000, maybe 1,000 entities, and then the selector took out 30 of them, or let's just say 35. So 35 gone. So 1,000 minus 35 is 965 entities. So in this case, the current population would be 965. Okay. And then what happens? Well, and then I would try to record these metrics, which is the head for as in the summed utility value of the top entity, the tail as in the summed utility value of the bottom entity, and the top 10%, 0.1, meaning the average of summed utility values of the top 10% entities within that generation. So if there were 965 entities, the top 10% of 965 is 96.5. I think I rounded that up, or maybe I rounded that down. So it's either 96, average of 96 entities, or average of 97 entities in terms of their summed utility values. And then what I do is I calculate the number of new entities to be created. So pop size was set to 1,000 initially. This is always 1,000, as the pop size is one of the hyperparameters. So 1,000 minus 965 is 35. And then we go through this. So if number of new entities to create is smaller than 0, we set that to 10, because we want things to keep growing. We want the population to not shrink. remember, this is what I've been doing so far. Now I have made the some improvements that I think I need. So, but right now this is not the case. We have 35 as the num create, which could be strange, but bear with me. And then for that amount of number, we go through a loop, for loop, and then we create the children by using the proc fx4, which is in my case so far has been the favoring highs, and then and every time I use this procreate function designated by this line, it will create two children, two new entities for 35 times. So that's 70 times. So all these children will be added to the current population, which is in the world. So 965 plus 70 would be 1030. And then we need to limit the population somehow, because 1000, the pop size, is only the initial population. It doesn't necessarily mean the maximum population. So right now the maximum population implicitly is set to 1400 because it's 1.4 times 1000. So we limit it by setting that. We limit it, but because we only have 1035, slicing it until 1400 is no problem. Everything is included, and then every entity, all 1035 entities will go through mutation, the mutation rate being 0.003. And then that's it. End of one generation. End of generation. And then we go back up to the next generation. Generation 2. Or maybe that was, if that was like generation 12, now we go to generation 13. All the way to generation 499, because it started with generation 0, so that's still 500 generations. But anyway, now here's the well, again, I just need to find a way to show all this. Maybe like this. Oh, that's too small. Can I keep it like this? Yeah, I think that, no. Maybe I could, no, I want a screenshot of all of this. Okay, I think that's good enough. Now back to 100. Cool. So here's the screenshot of how it is per evolution iteration. Per iteration. I know this is very small, so just bear with me. So back again. This part is the recording part, or storing values. From here to here is the ranking part. This part is the selector part, or striking things out. And this part is, well, this huge part is procreation, but within that procreation, this determines, or rather these determine how many to procreate in that generation. And once that's decided, we procreate or create new entities, and then which are added to the world, and then the population is just kind of controlled to the maximum population size, which is in this case 1.4 times population size, the hyperparameter. Yeah, and then we mutate. That was so far how it is right now. Okay, so we'll keep this here. Now let's go to the well, I can just go over all the variations that I did, but I don't think that would be wise. Or not. Let's just look. So here's the first file, first new file that I've made. It's called General Genetic Algorithm Grid Search Beta Evolution Normal 0. It's crappy naming, but crappy title. I'll change it, maybe. I don't know. So the first thing that I did, and actually the kind of one of the simplest things that I did, was I'm not actually like, if you look at here, if you look here, if we look at the peak plateau plot, we know that this part happens. These parts happen because no entities are being struck out, and because no entities are being struck out, this means that when the selector, well, I don't know if I might have this backwards, but let me just rephrase that. Because the selector is actually not doing its job, because it's not supposed to, because it's meant to do that, so no 0 entities are being struck out, which means that the population just always stays at 1000. If we started with 1000, we stay with 1000. Alright? And with the old way of doing things is that if the population size is 1000 and the current population is 1000, we get the num create at 0, and since I wasn't covering it when num create was 0, I was only covering it when it was either a minus or a plus. I didn't have all the cases covered. So one of the first things that I did was just put an equal sign there. That's number one. And also I realized that in my selector function, this actually didn't matter as much as putting that equal sign to the in the num create line. But what I actually also did to the selector function was that I added another equal sign here, because if you think about it, if the maximum constraint percentage is 100%, it should mean that you can take everything, and the total sum of constraints is actually something that you can, or every entity can support or withstand. But however, if there's only a bigger than or a smaller than sign here, it doesn't mean that. Everything, the sum of utility values for all, the sum of constraint values for all entities still have to be smaller than the max constraint, which is wrong. So I just put an equal sign here as well. Ultimately I did, and I had to mix and remix around the order of things, the order in which I do things in my evolution scheme, so that nothing is being done twice and everything is being done at about the right moment, at the right stage. So let me just take a sip of water. So I tried, so a couple of variations where I could, for example, use the selector first, which I still no, oops, where I could do the ranking first, and then record, of course, which is kind of minor. It's like a minor detail, and then do this, do the procreation, and then limit the whole thing. Oops. And then maybe select, and then mutate, something like that. So it's a different combination, but ultimately I found that the neatest way of doing it was something like this. Go away. So that's the first page. Oops. And then create. Yeah, there we go. Okay. So let's zoom in. So first what I do is I introduce the genesis into the world, so that's still the same. Yeah. I might still make a few tweaks here and there, but this is generally how it will go. Hold on, let me. Okay. So yeah, I might make a few changes, but in the meantime, and as I'm recording this, I just want to make sure that I have things right. So I'm going to rerun some bits of this code, so that it runs while I'm talking. Okay. I'm so bad at this. And done we go. And here, and rerun all the selected cells. Cool. So first, where is it? Okay. So we introduced the genesis into the world, and then we run the selector, although I don't think this is needed. Maybe it's a redundancy that I was willing to, somewhat unconsciously willing to, let it, willing to let exist, whatever. So anyway, so what happens is after that, I rank it. I rank everything, and then recreate the world. So all this is rank and recreate. That's a crappy ampersand. Recreate. I really need an iPad or something, drawing pad or something. And then I get the number for the current population, and then I record the values for this generation, record these values for this generation. I calculate the number to create, num create, and if the num create is smaller or equal to 0, the num create becomes population size, pop size times 0.03, which is 3%. And well, this is like a TLDR, like a spoiler. So this so far is the best performing in quotes. I'm doing the air quotes, the fingers. But anyway, and I procreate here. Yeah. Which is so for maybe, just suppose it was, just suppose that the current population is 1000. So num create was 0, which means that num create will become 30 over here. So for 30 times, we create 2 children, which would give us 60 children. All these 60 children are put into the newborns list, and then we select newborns at random for how many? Well, maybe half of them, but with duplicates. And then we introduce them into the world, but at the front. This is very important, introducing them at the front, because so far the pre-existing world, after being ranked and recreated, all these entities have been ranked, and if the newborns are attached here or appended here, if I limit the population, for example from here to here, from here to here, these guys will be gone. Or maybe if I were to limit all the way down to here, these guys will be gone. So only these new offsprings, which are actually from most of them, or mostly from these entities, are gone. So there's little innovation there. So what putting the newborns at the front does is that, since they're at the front, it looks like this. And what this does is that because these guys, well, the parents of these guys are probably these guys, or these guys, or these guys, whatever, because I'm using favoring highs, the parents are more likely to be one of the top entities. It's not oligopoly, but still, it's a lot kind of similar to oligopoly parent selection scheme. So the newborns stay for sure, because they when I limit the population, maybe down here, the newborns stay because they're at the front, and the entities with sadly low summed utility scores will be left out, will be excluded. They won't be passed down, which is sad, I know. Yeah. And then this new world will be passed on to the next generation after it goes through mutation. So every entity, well, yeah. So every entity so let's do that again. We have the new entities. No, we have the old world with old entities, and then we have the new entities like that, let's say, and then we these are the new entities, these are the old entities, and they all go through mutation. So even these entities that are likely to be higher in terms of some utility values can go through mutation and be struck out by the selector function, which of course doesn't happen because at very high levels, or maybe when maximum constraint percentage is at 100%, it will never happen. But anyway, it still is subject to mutation, like, you know, as seen here. And then when that happens, we select again. Nothing gets struck out because nothing gets struck out when max constraint percentage is at 100%, or almost nothing gets struck out when it's at 90 or 95%. And then we limit the population. And what else? What else did I change? So hold on. And all of this for 20 max constraint percentages take about 26 minutes. People talk a lot. Yeah, awesome. Cool. Yeah, so it's about the same. Turns out, again, I'm correcting myself in my video log, but turns out that I don't need this either. I knew I didn't need this. It's just that this stayed as a mistake, but I don't know if I'll keep this or not. You know, it doesn't seem to make much of a difference. It will make a lot of difference, huge difference if things get bigger. But yeah, I don't need the very first selector being applied here, because the last one does it at the end after the mutation. Now putting the mutation, let's just, what? No. Where is it? I'll just copy this. What did I do? Just erase everything. No, here. There's a reason. There's kind of like a philosophy to why I put the mutation there. And then I use the selector, and then I limit the population. Is that even when the newborns are added to the world, you could just I could just put this right here and then mutate. But the logic or the philosophy here is that before every generation ends, I just thought it would be nice for every entity to have, you know, for many of the entities towards the lower end, to have a chance to mutate so that they can move a bit higher, and the entities at the top to mutate for the better or for the worse, or to be struck out. And then when it's done, we use the selector to assess the results of the mutation of that generation, and then we limit it. So if the max constraint percentage was set to like something like 80%, some entities will be struck out by this after the mutation. Even the top ones will be struck out. And then if it still goes above the maximum population, it'll be cut, and then this part will be passed on to the next generation to rinse and repeat. So that's the thing. So here's a quick preview, well, like an overview of what happens when you do it, but it depends on what values I give to maybe the percentage of it depends on what value I give for new entities percentage, which is what percentage of the newborns are selected and added on to the world. Also, it also depends on the number to create, as in this number 0.003 or 0.05. So it's either 3% of the population size or 5% of the population size. Population size being one of the hyperparameters, and the overall runtime, the time it takes to run this, also varies depending on what number I put in as the maximum population. Right now it's set to 1.0, but I usually set it to 1.4, as seen here in one of my previous notebooks. And what this does is something like this. These plots are only for when the max constraint percentage is at 95 and 100%. I just did this to save time, and this is what you get when you run it for the entire 20 maximum constraint percentage values. Yeah, and as you can see, the red line being the total sum of utility, and the yellow one is the peak level, the blue one is a plateau level, and in this case the peak level, the average peak level, is above 3900, 3800, above 3700, whereas the average plateau level goes way up to above 3600 in this case, for the numbers I put in for different parameters, for values. However, in my last run of the code, or in one of the last runs of my code, this is what happens. Yeah, let's see that. So this is after randomly choosing from all the newborns, allowing duplicates, and then introducing the chosen ones into the world. Yeah, this is how it goes. And depending on what number I put in again, the peak level, the average peak level, can also go up to 3800, and the average plateau level can go up to slightly below 3800. I think this is when I sampled was it like 60% of all the newborns or something like that. I still have to figure it out, but I think for now choosing half of all the newborns is a kind of like a safe bet. And running this would take about 20, so 123 seconds times 10, 125 seconds times 10, so that's 125 times 10 is, and then I need to divide that by 60. I don't know why. Oh yeah, I was running anything, was I? Yep, thank you. That's 20 minutes, 21 minutes. So 21 minutes, which is a lot of saved time. And also I did make some few tweaks and adjustments to the code so that, allegedly it's supposed to be, faster. And also I was limiting the population size to population size itself. I could make this 1.4 back again. I could make this percentage go up or down. I can make it just at 1 as well, which would greatly boost the peak plateau plot like this, but I don't really see the point there. Well, if I were to allow 100% or the same number of entities as the number of entities actually created from procreation, but by randomly choosing and allowing for duplicates, it means that I'm actually throwing away not allowing some of the new entities to be passed on to the next generation, which just sounds cruel. But then again, randomly choosing, allowing for duplicates and randomly choosing is also cruel. So it's a dilemma. But one very interesting thing was, one very interesting thing to note was that just simply adding all the newborns, introducing all the newborns to the world, doesn't actually raise the average peak level and the plateau level towards the end. This always happens. It kind of falters off like that, and I guess it's again the power of randomness. So what you do, or rather what you get when you use favoring highs, is that you'll get entities procreated by parent 1 and parent 2 who are very likely to be amongst the higher performing entities, and therefore they will be better, in quotes, in some sense. Again, I don't want to go on about what is good, better, or best, or what is bad, worse, or worst. It depends on the situation. I'm trying to make something that can adjust to these changes in the circumstances and in the situation, in the environment, so I don't want to talk about that anymore right now, but you get the point. So somehow that wasn't happening. However, when I started randomly choosing, allowing for duplicates from the entire list of the newborns, and then saving those in the selected new entities, which is the list, and adding that to the world, it worked. So well, I don't want to just say, oh, it worked. It produced somewhat better results for now. So I'll be using this from now on until I see some other problems with it, and I'll fix that problem when I see it. But in the meantime, yeah, next up is I'll just be going in my next video. I'll including the stuff I did today or tomorrow, that I covered today. I'll try to see if this behavior is the same for all the 8 distributions. When each and every one of these 8 distributions is used for the utility values and the constraint values. And then if they are the same, then I don't think I need to go through all 64 distribution products. If I can just confirm, if I can just confirm that given the new evolution scheme, given the new evolution scheme, if I can just confirm that they will all be like this, you know, allowing for some dips towards the end, but if they'll all be like this, I wouldn't need to do this again. If they were all like this for all of the 8 distributions, when those 8 distributions are used for the utility values and the constraint values, I don't know why you start writing with an S first. Constraint values. If they behave the same way, I don't need to do all 64. I don't think I need to do all 64 distribution products. But then again, even if that does happen, I might end up doing it just out of curiosity, or just, you know, for the sake of trying out some other Jupyter Notebook platforms, online platforms that allow me to run 24/7 without runtimes being interrupted. But yeah, so that's what I'll do. And then next, I'll need to find the right combination of procreate functions. And then I might even go back to using the vape juice, the MacBook, the pre-made items and pre-made utility values and pre-made, arbitrarily pre-made constraint values, the ones that I had before, and then also move back onto general genetic algorithms, meaning generated values using the function that I made. Yep, I think that's the plan for now. That's it. Oh, that was 52 minutes. Okay, thanks for watching. Bye.